Today, we are taking a massive stack of incredibly dense physics sources. We're talking foundational papers on quantum superposition, the Copenhagen interpretation, Schrödinger's cat, and the many worlds interpretation.
Oh yeah, it is quite the stack. Really heavy reading.
It is, right. But we are synthesizing it all for you. Our mission here is to act as your shortcut to being well-informed on this topic.
Exactly.
We are going to explore the bizarre dual nature of reality at the subatomic level, figure out what actually happens when we attempt to observe it, and we'll unpack the mind-bending theories physicists have created to explain how our universe functions.
It's honestly a total paradigm shift from how we usually experience the world.
It really is. Okay, let's unpack this. Because to get there, we need to talk about an assumption of permanence. You know, when we walk outside at night and look up at the sky, there's this fundamental assumption we all make about reality.
Right, that things are just there.
Exactly. You look at the moon, you see the moon, you close your eyes, and you just know with absolute certainty that this giant rock is still floating up there in the dark.
Yeah, I mean, it's the bedrock of how we navigate the physical world. Objective reality, the idea that things exist independently of us looking at them. Like, if a tree falls in a forest, it makes a sound, and the moon is there even when you turn your back.
But then you step into the world of quantum mechanics, and suddenly that bedrock it completely vanishes.
Poof. Gone.
We are looking at a landscape of reality that fundamentally challenges whether the moon is actually there when you aren't looking at it.
Which sounds like magic, but when you get down to the subatomic level, the universe stops behaving like a collection of solid objects. It starts behaving like a casino where the rules are written in a language we are barely beginning to translate.
And we can't really grasp the wild interpretations of this reality until we understand the core phenomenon causing all this fuss, which is quantum superposition.
Right. And everything starts with the math there, specifically the Schrödinger equation, which was developed back in 1925.
Okay, 1925. Got it.
Yeah, and this equation determines the state of a quantum system. The key thing to understand about it is that it's linear.
Meaning what exactly?
So in mathematics, if you have a linear differential equation, it means that if you have two valid solutions, you can just add them together to create a linear combination.
Oh. Okay.
And that combined result is also a perfectly valid solution to the equation. So before you make a measurement, quantum systems, like the qubits used in quantum computing, they exist in this linear combination. It's a superposition of states.
Right.
If one valid state is 0 and another valid state is 1, the math says the system isn't just 0 or 1, it is a combination of 0 and 1 simultaneously.
So it's not like mixing yellow and blue paint to get green paint where it becomes a totally new single thing. Is it more like, I don't know, a spinning coin?
Just spinning coin.
Yeah, like it's not heads or tails while it's spinning. It's a blur of both probabilities until it slaps onto the table.
What's fascinating here is that your spinning coin analogy is brilliant for visualizing the blur, but quantum mechanics adds a twist that defies classical logic.
Oh.
Think about a normal spinning coin. In classical physics, the coin is spinning, and we just don't have enough information to know which side is facing up at any given microsecond.
Right, it's moving too fast for our eyes.
Exactly. The uncertainty is entirely in our own heads. It's our own ignorance. But in quantum mechanics, the math doesn't say we simply don't know the state. It says the particle is literally, physically, in an intermediate state governed by probabilities.
Okay, wait. How do we get from a physical blur of math to an actual probability of something happening in the real world?
That bridge between the abstract wave and a physical measurement comes from something called the Born rule.
Proposed by Max Born.
Yes, exactly. Max Born. The Schrödinger equation gives us a wave function, which has an amplitude. You can think of it as the height of the wave. Max Born realized that if you take that amplitude and square it, it gives you the exact probability density of finding the particle in a specific location or state.
Oh, wow.
So the math isn't just tracking a particle's path, it's tracking a wave of pure probability. The superposition is its actual physical reality until observed.
That is wild. It is physically in a state of both and neither.
It really is. And this has been proven repeatedly through the famous double-slit experiment.
Oh, I've heard of that one.
Yeah, you fire particles like photons or electrons at a barrier with two slits. When not observed, they act like waves, passing through both slits simultaneously. Because they go through both, the waves overlap and create an interference pattern on the screen behind them.
Like ripples in a pond.
Exactly like ripples in a pond.
Yeah.
But the moment you place a detector at the slits to see which one the particle actually goes through, the wave behavior completely vanishes. It acts like a solid bullet and goes through just one slit.
Just because we looked.
Just because we looked. As the Nobel laureate Anton Zeilinger pointed out, this interference pattern is destroyed if the path information is even accessible in principle.
Accessible in principle.
Yeah, meaning even if no human is actually looking at the data, the mere fact that the universe recorded the path destroys the superposition.
Okay, so since the math tells us the coin is definitively spinning in a wave of probability, what exactly causes it to slap onto the table and pick a side? I mean, why does reality suddenly choose a path just because information became accessible?
Well, that exact question led the pioneers of quantum physics in the 1920s to form the first major framework to explain this weirdness. We call it the Copenhagen interpretation.
Named after the city where Niels Bohr and Werner Heisenberg were doing a lot of their heavy lifting, right?
You got it. Heisenberg actually coined the term Copenhagen interpretation decades later, though doing so glossed over some pretty massive disagreements he had with Bohr.
Oh, they disagreed.
Oh, absolutely. But the core concept they did agree on was that quantum mechanics is intrinsically indeterministic. It's not that we lack information, it's that the universe itself hasn't decided yet.
That is deeply unsettling.
They posited that an act of measuring an object is an irreversible process. When you measure it, you cause the wave function, that spinning blur of probabilities calculated by the Born rule, to violently collapse into a single actuality.
So the coin slaps down.
Exactly. Heisenberg preferred the term reduction over collapse, but the idea is the same. The potentiality becomes reality through the act of measurement.
But how do they define a measurement? Where's the line? Because aren't physicists and human eyeballs and heavy laboratory equipment all made of the exact same subatomic matter as the rest of the universe?
Yes, they are.
So if an electron is a quantum blur, and I am made of electrons, how can there be a magical boundary where standard quantum physics just stops and classical physics begins?
You've hit on the exact logical vulnerability that has haunted the Copenhagen interpretation for a century. You just described what's known as the Heisenberg cut.
The Heisenberg cut.
Yeah, it's this completely arbitrary boundary between the quantum system being observed and the classical measuring device doing the observing.
And I'm guessing physicists don't love arbitrary boundaries.
Not at all. And Bohr and Heisenberg actually disagreed on where this line should be drawn. Bohr thought that the physical, macroscopic setup of the experiment dictated where this cut was. He thought the heavy machinery was fundamentally classical.
And Heisenberg?
Heisenberg believed that the observer had the mathematical freedom to shift that boundary arbitrarily. You could include the measuring device in the quantum system, treating the device itself as a superposition, and then the cut is placed between the device and the human observer.
That sounds incredibly messy. It feels like they're just drawing a line in the sand, closing their eyes and saying, don't look past here. The mass breaks.
Albert Einstein felt exactly the same way. He found the indeterminism deeply philosophically troubling, which led to his famous quote, "God does not play dice."
Right, because he fiercely believed in objective reality.
He did. Abraham Pace, a fellow physicist, recalled a walk he took with Einstein where Einstein suddenly stopped, turned to him, and asked if he really believed that the moon exists only when he looks at it.
Ah, the moon. We're back to the moon. Einstein wasn't buying the idea that our observation is what manifests reality.
Not for a second. He fundamentally rejected the idea that a conscious observer or a macroscopic piece of metal in a lab possessed some mystical ability to collapse the laws of physics.
Makes sense.
And in 1935, another brilliant physicist wanted to highlight just how ridiculous this idea of the Heisenberg cut was if you scaled it up from the subatomic level to our everyday macro world.
Enter Erwin Schrödinger, and a very unfortunate hypothetical feline.
The most famous cat in science.
Let's look at this setup. In 1935, Schrödinger proposes this thought experiment, and it actually comes out of a letter exchange he was having with Einstein regarding that exact frustration over the Copenhagen interpretation.
The EPR paper correspondence, yes.
Right, so Schrödinger designs this setup, which he literally calls an infernal device. He envisions taking a sealed steel chamber. Inside this chamber, you place a live cat.
And this is purely a thought experiment, we should stress.
Oh, absolutely. No actual cats were harmed.
Yeah.
You also put in a tiny amount of a radioactive substance, so tiny that over the course of an hour, there is exactly a 50% chance one atom will decay and a 50% chance no atoms will decay.
So it's perfectly balanced on the quantum edge.
Exactly. You hook up a Geiger counter to monitor the radiation. If the counter detects a single decayed atom, it triggers a relay, which drops a hammer, which shatters a small glass flask of hydrocyanic acid, releasing poison and killing the cat.
It is a brilliantly constructed, if macabre, mechanism because it ties a single quantum event, the decay of one atom, directly to a macroscopic everyday outcome, which is the life or death of the cat.
Exactly. So, according to the Copenhagen interpretation, before you open the box to look, the radioactive atom is in a superposition of both decayed and not decayed. Therefore, the trigger is both pulled and not pulled. The poison is released and contained. And the psi function of the entire system, as Schrödinger wrote, contains a living and dead cat mixed or spread out in equal parts.
A macroscopic blur of life and death.
Wait, so Schrödinger didn't actually believe the cat was dead and alive, right? He wasn't proposing a literal zombie cat floating in a steel box.
Absolutely not. And that remains one of the biggest misconceptions in popular culture. This was a reductio ad absurdum.
A joke to prove a point.
Exactly. It was a deliberately farcical joke meant to show how ridiculous Bohr's model of reality becomes when an atomic indeterminacy is scaled up. Einstein actually wrote a letter to Schrödinger in 1950 praising him for this thought experiment.
Oh, he did?
Yeah, he said it elegantly refuted the Copenhagen interpretation. Because, as Einstein pointed out, nobody really doubts that the presence or absence of the cat is independent of the act of observation. The cat is fully conscious. It knows if it's alive.
Right. The cat is an observer, too. It just highlights how poorly defined this Heisenberg cut really is. So, if Copenhagen leaves us with these absurd zombie cats and an unexplained magical collapse of the wave function, the second the human peeks inside, is there an interpretation of the math that doesn't require the wave function to collapse at all?
Well, to get rid of the collapse, you have to accept an idea that sounds even more like science fiction.
Okay, I'm ready.
In 1957, a PhD student at Princeton named Hugh Everett proposed what he called the relative state formulation.
Doesn't sound too sci-fi yet.
Give it a minute. Later, a physicist named Bryce DeWitt popularized it and gave it the name we all know today, the many worlds interpretation.
So what does this all mean? How does many worlds deal with the cat in the box?
In Everett's view, the universal wave function is objectively real, and there is absolutely no collapse.
Not at all.
None. The Schrödinger equation applies to everything, all the time, from the smallest electron to the largest star, including the observer. So what happens when the box is opened? The observer looks inside and interacts with the system. This interaction leads to a physical process called decoherence.
Decoherence, meaning the superposition breaks down.
Not breaks down, but leaks out. Think of it like dropping a single drop of ink into a swimming pool.
Okay, I'm picturing it.
The ink doesn't vanish, it just becomes so wildly entangled with the massive environment of the pool water that you can no longer track it.
Ah, I see.
When the quantum system interacts with a messy macroscopic environment like air molecules bouncing around or body heat from the observer, the quantum information leaks out.
It gets scrambled.
Exactly. The delicate phase relationships between the superposed states get scrambled. The observer and the cat become quantumly entangled, but the wave function doesn't collapse into just one outcome. Instead, the universe splits into non-interacting branches.
Okay, let me see if I have this right. It's like a choose-your-own-adventure book, where instead of making a choice and turning to page 42, the universe prints two separate copies of the entire book, and different versions of me read both pages simultaneously in parallel universes.
That is a highly accurate way to look at it.
Wow.
There is a branch of reality where an observer opens the box and is horrified to see a dead cat. And there is an equally real branch where an observer opens the box and is relieved to see a living cat.
Both are real.
Both are equally real, but because of decoherence, because that ink has permanently mixed into the water of their respective realities, they can no longer interact or communicate with one another.
That is mind-boggling.
It is, but what's elegant about this mathematically is that it makes the universe completely deterministic and dynamically local. There's no spooky, instantaneous collapse. Everything evolves smoothly according to the math.
But isn't that totally unscientific? I mean, a core pillar of science is falsifiability. How can we test for parallel universes we can't communicate with?
That's the big criticism, for sure.
Right, like if we can never interact with the other branch, isn't it just a philosophical belief?
Well, if we connect this to the bigger picture, it might actually be testable, though the engineering required is currently beyond us.
How so?
In 1961, physicist Eugene Wigner proposed a thought experiment known as Wigner's friend, which highlighted the paradox of subjective measurement.
Wigner's friend.
Yeah, so Wigner's friend is inside a lab measuring a particle. To the friend, the wave function collapses. But to Wigner, standing outside the closed lab door, the friend and the particle are in a combined superposition of all possible outcomes until Wigner opens the door.
So the friend is the cat in this scenario.
Basically, yes. And decades later, in 1985, physicist David Deutsch took this further to propose a physical test for many worlds.
How do you physically test a parallel universe?
By replacing Widner's human friend with an advanced artificial intelligence running inside a massive, perfectly isolated quantum computer.
Okay, sci-fi level unlocked.
You put this conscious AI into a superposition. The AI makes a measurement of a quantum spin, which branches its reality into two states, one where it saw spin up and one where it saw spin down.
Right.
Here is the trick. An observer outside the computer then carefully reverses the unitary quantum operations of the computer.
Wait, reverses it?
Yes. They don't ask the AI what result it got, which would cause decoherence. They just reverse the measurement process itself, recombining the two branches to see if they create an interference pattern.
So if Copenhagen is right.
If Copenhagen is right, the wave function irrevocably collapsed the moment the conscious AI looked at the spin. Reversing the operation won't produce an interference pattern because only one reality survived the collapse.
And if many worlds is right.
If many worlds is right, both branches of the AI actually existed. When you reverse the operation, those two parallel realities will recombine and interfere with each other, proving that multiple realities were happening simultaneously inside that computer.
Wow. So many worlds solves the measurement problem because there is no measurement problem.
Precisely.
There's no magical boundary. Everything is just quantum mechanics, all the way up.
It completely removes the arbitrary collapse rules that troubled Einstein and Schrödinger. The math just plays out exactly as it is written, scaling infinitely.
So taking this out of the realm of thought experiments and into the lab, scientists are actually building Schrödinger's cats today, right?
Oh, yes. Not literal cats, thankfully.
Obviously not cats. But they are creating superpositions of larger and larger objects. It started with photons and electrons, but the scale of modern superposition experiments is incredible.
It really is.
I read they've successfully put buckyballs, which are these large carbon molecules, into superposition, and they've superposed massive molecules called functionalized oligoporphyrins that are made up to 2,000 atoms.
The jump from single subatomic particles to 2,000 atoms is a staggering engineering achievement.
Truly.
It proves that superposition isn't just a quirk of the very, very small.
And it gets bigger. There's a mind-blowing experiment where scientists created a piezoelectric tuning fork comprising roughly 10 trillion atoms.
Yeah, that one is amazing.
10 trillion. And they placed it into a superposition of vibrating and non-vibrating states simultaneously. You could practically see this thing under a standard microscope, and it is physically existing in two states at once.
That is essentially a mesoscopic Schrödinger's cat. And this isn't just about showing off, this is the fundamental architecture of the future of technology.
How so?
Well, in quantum computers, physicists create what are literally called cat states, a prime example being the GHZ state.
The GHZ state, what's that?
It stands for Greenberger-Horn-Zeilinger. Instead of just putting one single qubit into a blur of 0 and 1, a GHZ state perfectly entangles 3 or more qubits together into a massive combined superposition.
Like tying the spinning coins together.
Yes. If you measure 1 and it comes up 0, the others are instantaneously 0. If it comes up 1, they are all 1. It is a highly fragile state where multiple particles exist in a blur of all being 0 and all being 1 at the same time.
Wow.
Achieving this state is vital for the future of quantum error correction and cryptography.
Harnessing the blur. But it sounds incredibly fragile. I mean, if just a tiny interaction with the environment causes decoherence, how do you build a reliable computer out of this?
That is the ultimate bottleneck. Controlling these superpositions without unintended interactions is the single biggest challenge in quantum computing today.
Because it just leaks out.
Exactly. Because, as we discussed with many worlds, interaction causes the quantum information to leak out into the environment. If a stray photon or a slight fluctuation in heat from the room bumps into your tuning fork or your delicate GHZ state, it acts as an observation.
And it collapses.
Or decoheres, yeah. The environment measures the system, the superposition decoheres, and you lose all that incredible parallel computing power. You have to isolate the system perfectly from the rest of the universe while still somehow being able to input and extract information.
It's like trying to perfectly balance a spinning coin on its edge during an earthquake, while also trying to read the date printed on it without knocking it over.
That is a very apt description of a quantum engineer's daily headache.
So what happens when we take all of this subatomic weirdness, all these mesoscopic cats and branching timelines, and apply it to our everyday lives? Think about what this means for the device you're holding right now.
The implications are everywhere.
The encryption that secures your bank account, the microchips in your phone, the computing power of the next century that might model complex molecules to cure diseases. All of it hinges on this bizarre principle where things can be two things at once until they interact with their environment.
Yep.
It proves that the universe is far stranger and honestly far more imaginative than our daily macroscopic lives suggest. We walk around feeling solid, but we are made of blur.
We are built of probabilities, masquerading as certainties.
Here's where it gets really interesting. Let's take this all the way to its most extreme logical conclusion.
Oh boy.
If we go back to the many worlds interpretation, there is a thought experiment known as quantum suicide or quantum immortality.
This is a dark one, but mathematically fascinating if you follow Everett's logic to the letter.
Imagine you are the cat. Or rather, you put yourself in the box with Schrodinger's infernal device. You hook a gun up to a quantum trigger, a spin measurement of a particle. 50% chance the gun fires and kills you instantly. 50% chance it just clicks and you live.
Okay.
If Copenhagen is right, you have a 50-50 shot of surviving each time you pull the trigger. Eventually, your luck runs out, the wave function collapses against you, and you die.
The probabilities catch up with you.
Right. But Many Worlds paints a completely different picture of your subjective experience.
It does.
If Many Worlds is right, the universe splits every time you pull the trigger. In one branch, you die. In the other, you hear a click. Now, from the perspective of the dead version of you, experience just ceases. You don't know you died.
Right, there's no consciousness there to observe it.
Exactly. But there is always a branch with a gun click. And from the subjective perspective of your own consciousness, you will only ever experience the branches where you survive.
Which is wild to think about.
You could pull the trigger 1 trillion times, and while there are 1 trillion universes mourning your death, you will just hear 1 trillion clicks.
Yeah.
You would conclude that you are functionally immortal.
It is a deeply unsettling implication to leave you with.
It really is.
If every possible outcome happens in some branch, and your consciousness can only follow the paths where it continues to exist, well, from your own perspective, in a many-world universe, you might just be immortal.
Incredible.
You can never empirically prove many worlds to anyone else with this method. They'll just see you die in their branch, but you will constantly prove it to yourself by surviving impossible odds.
That is going to keep me up tonight. And the next time you walk outside and look up at the moon, just remember, the only reason it looks so solid, so undeniably there, is because you and the entire environment are constantly entangled with it, locking it into place.
It's all connected.
Close your eyes and let the blur take over. Thank you so much for taking this deep